We often think of the quantum world as this tiny, almost invisible place.
Right, separate from our everyday experience.
Exactly. But then you get phenomena like the Casimir effect, and suddenly these quantum jitters, they sort of bubble up into our world.
It's fascinating.
You take two perfectly normal, uncharged surfaces, put them super close together, and, well, they attract each other.
Just from empty space, supposedly.
Yeah, it's all down to these vacuum fluctuations, tiny particles popping in and out of existence. Casimir himself worked out the math for parallel plates, and the force scales pretty dramatically, doesn't it? Inverse fourth power of the distance.
It does. And it's amazing how something so abstract, these virtual particles, have real measurable effects. Especially at the nanoscale, it becomes a significant force. I mean, proving it experimentally was tough for decades. You need such incredible precision to isolate just that force.
Right, away from everything else happening down there.
But yeah, now it's a well-established thing, fundamental for nanotech.
Absolutely. Which, leads to the next question. What happens if you mix it with another quantum giant?
Like superconductivity.
Exactly. What if those surfaces become superconducting, lose all electrical resistance below that critical temperature T setter? Both are these amazing macroscopic quantum effects, but how they interact, well, that's been experimentally elusive. Until now, it seems.
It's a really fundamental question. Superconductivity means a radical change in the material's electronic properties right at TC.
So it changes the boundary conditions for the Casimir effect.
Potentially, yes. And measuring any change in the force across that transition could tell us something really deep about how these phenomena connect.
But actually doing that measurement, the paper makes it clear it sounds incredibly hard.
Oh, it is. Monumentally difficult.
You need nanometer level parallelism, but at cryogenic temperatures.
Any tiny misalignment ruins the measurement.
And you have to measure across TC without, disturbing the superconductivity or the force you're trying to measure.
Plus, you have to filter out everything else. Thermal expansion as things cool down, any stray electrostatic charges. Figure 1b in their paper really spells out the sheer number of potential confounding factors.
Yeah, it's a minefield.
Which is why this new study is so interesting. Their whole approach was about finding a way through that minefield to finally measure the Casimir force across the superconducting transition. That innovative experimental design is really the core of it.
Okay, so let's get into that. We've talked about why it's important fundamental physics, maybe even hints about gravity, the whole Drude versus plasma model debate.
Right, those are the big theoretical drivers. Understanding how the metal's optical properties, whether they act more like a Drude model with scattering or a dissipationless plasma model, affect the Casimir force is a long-standing question.
And seeing a change across TC could help settle that.
That's the hope. Previous experiments just didn't have the sensitivity to tell the difference between the model's predictions near TC.
And the gravity connection, that sounds pretty wild.
Well, it's definitely more speculative. Some theories suggest superconducting Casimir setups might interact with gravity in non-classical ways, but let's be clear, that's very much unverified territory.
Fair enough. What about the idea that the Casimir force could influence the superconducting transition temperature itself, especially in those high TC superconductors?
That's another interesting angle. Some high TC materials have layered structures, almost like built-in Casimir cavities. There's this open question about whether the vacuum fluctuations within those tiny gaps could actually help stabilize the superconductivity, maybe even push TC higher.
Huh. Any evidence for that?
There was some older experiment decades ago with alternating superconducting and insulating layers that hinted at something similar, some kind of interaction-enhancing superconductivity. But directly linking it to the Casimir effect in a controlled way is tricky.
Okay, so a lot of deep questions hang in the air, which brings us back to this experiment. How did they actually manage to measure this? What was the big innovation?
The main breakthrough, I'd say, is their use of an on-chip, fixed-gap parallel plate geometry.
Which is closer to Casimir's original idea, right? But harder than the usual sphere-on-a-plate setup.
Much harder, yes. Sphere plate is easier to align. But for the precision they needed and to really probe the theory accurately, parallel plates are better. The innovation was figuring out how to make it work reliably on a chip.
How do you get things that parallel?
Advanced microfabrication, they use these special high-stress niobium titanium nitride NB10 membranes. Think of them like tiny, incredibly taut drumheads.
Okay.
And the gap between them isn't set by manually pushing things together. It's defined lithographically during the chip manufacturing process. It's fixed from the start.
Ah, built-in parallelism.
Exactly. And the level they achieved is just staggering. Figure 2 shows it. They report a sag of only about 142 picometers over nearly 710 microns. That's an angular misalignment of like 200 thousandths of a degree.
Wow, that's incredibly flat.
It really is. They state in the paper that this area to separation ratio is unprecedented for Casimir experiments, especially at cryogenic temperatures. A major leap in control.
Okay, parallelism solved, but how did they isolate the Casimir effect's change from, say, the material just changing properties as it got colder?
Very clever trick. They used a dual chip setup.
Two experiments at once.
Sort of. On the same holder, cooled together, they had two identical devices. One had a tiny gap, 190 nanometers, where the Casimir force is strong. The other had a much bigger gap, over 1200 nanometers, where the Casimir force is negligible.
Ah, a control group built right in.
Precisely. Since both chips experience the exact same temperature changes, the same vibrations, the same vacuum, any changes common to both, like thermal expansion or changes in the material's stiffness, can be subtracted out.
So you compare the small gap chip's behavior to the large gap one.
And anything different in the small gap chip near TC must be due to the Casimir force changing. It's a differential measurement, really crucial for isolating the effect.
Okay, that's smart. So they have this incredibly parallel, stable setup with a built-in control. How did they actually measure the tiny movements or force changes on the membrane?
They use scanning tunneling microscopy, STM.
STM. Isn't that usually for looking at atoms?
It is, but the principle it uses is perfect here. The tunneling current between the sharp STM tip and the membrane surface depends exponentially on the distance.
So tiny distance changes mean big current changes.
Huge changes, they position the tip incredibly close, less than a nanometer away, but not touching. The membrane vibrates, maybe only 30 to 100 picometers.
Which is minuscule.
Tiny. But because of that exponential dependence, the STM can pick up those vibrations easily by monitoring the tunneling current. It's exquisitely sensitive displacement sensing.
And it doesn't really push on the membrane or mess with the superconductivity.
Exactly. It's non-contact, non-perturbative. The feedback loop keeps the average gap constant, and they measure the oscillations in the current. They even manage to keep the interaction zone super small, like 10 picometers wide, minimizing any disturbance. Figure 3A shows the whole setup: UHV, cryo, the voltage drive to make the membrane oscillate, and the STM reading it out.
Plus all the work to cancel stray electric fields and account for van der Waals forces.
Right, using that differential measurements again for things like thermal expansion. Integrating STM this way for this kind of measurement is another really key innovation.
Okay, so they built this incredible machine. What did it tell them? What did they actually see happening at the superconducting transition?
The payoff was clear. Looking at figure 4A, they saw the resonant frequency of the membrane in the small gap cavity take a much sharper dip, a distinct feature right around TC, about 14.2 Kelvin for their NBT.
But not in the large gap cavity.
Much less pronounced in the large gap one. Since the Casimir force is only strong in the small gap, this sharp feature was the smoking gun. Superconductivity was definitely changing the Casimir force.
Directly linking the pair.
Yes. Then they carefully analyzed the square of the frequency shift, calibrating out the normal temperature dependence of the membrane's elasticity using the large gap data. Figure 4B shows the result: clear contrasting behavior between the two gaps right at TC. This quantitative analysis was vital.
And could they put a number on the force change?
They could. They calculated the frequency shift corresponds to a Casimir force change at the FCS, about minus 0.33 nanonewtons.
Minus, so the force decreased.
Careful with the sign. A negative FTT is here actually means the attractive force increased as the temperature went up through TC, from the superconducting state to the normal state. Same for the pressure change, FTC, about minus 0.65 millipascals. The pressure also increased as it became non-superconducting.
Okay, got it. An increase in attraction when superconductivity switches off. How did they connect frequency to force?
They used the standard Lipschitz theory to calculate the expected Casimir pressures based on material properties, and then finite element simulations to translate the measured frequency shifts into force changes. It's a rigorous connection.
Right. And the big question, how did this match the theories? Did it help with that Drude versus plasma model debate? This seems like where the innovation really pays off in terms of insight.
Absolutely. This is where it gets really interesting. They compared their results, specifically how the gradient of the Casimir pressure changes with temperature across T theta, to predictions using different models. They used BCS theory for the superconducting state, which is standard. But for the normal state, they tested both the Drude model, which includes electron scattering or dissipation, and the simpler plasma model, which assumes no dissipation.
And which one fit?
The results, particularly that jump in the pressure gradient right at TC, shown in figure 4C and the supplementary figures, were much more consistent with the predictions using the plasma model for the normal state combined with BCS for the superconducting state. The plasma BCS approach matched the data significantly better than Drude BCS.
So this experiment provides pretty strong evidence for the plasma model being the better description here, at least for how NB10 interacts with vacuum fluctuations near TC.
It seems so. They point out that one part of the Casimir force, the TM polarization, doesn't really explain this jump. It's the other part, the TE polarization, where the Drude and plasma models differ significantly in their predictions at low frequencies, and the plasma model's prediction fits what they saw.
Huh. That's a concrete step forward on a long-standing theoretical puzzle.
It really is. And underpinning all this was the incredible quality of their resonators. They mentioned achieving very high quality factors, Q, even at cryogenic temperatures, which means the resonance peaks were very sharp and easy to track precisely. That sensitivity, detailed in the supplementary info, was crucial. High Q is another mark of the platform's quality.
So this innovative platform didn't just make the measurement possible, it made it precise enough to start distinguishing between fundamental theories. What about looking forward? What else could this setup be used for?
Well, the researchers themselves point towards broader implications. The sheer parallelism and sensitivity make it a promising platform for developing new kinds of nanoscale sensors.
Ultra-sensitive detectors.
Potentially. Also, having such a well-controlled high-Q mechanical system operating at cryogenic temperatures could be a boon for tabletop experiments searching for subtle effects related to fundamental physics, maybe even exploring quantum gravity ideas in the lab.
Really? Tabletop gravity tests?
It's a long shot, but platforms with this level of precision open doors. And for condensed matter physics, it's a new tool to precisely probe surface forces and material properties right across phase transitions like superconductivity. It's just a leap in what's experimentally possible in this area.
So wrapping this up then, it sounds like this study is a major milestone. They finally managed to measure how the Casimir force changes on a material becomes superconducting.
Definitely. A long-standing challenge overcome.
And the key was really the innovation in the experimental design, that on-chip, fixed-gap, ultra-parallel setup, combined with the incredibly sensitive, non-invasive STM readout.
Those were the crucial elements, yes. Tackling immense technical hurdles with genuinely novel approaches.
And beyond just making the measurement, the results provide real quantitative data that helps refine our understanding of these quantum effects, strongly favoring the plasma model over the Drude model in this context.
Right. It's a fantastic example of how pushing experimental boundaries through real innovation in design and technique leads directly to deeper fundamental insights. It connects the dots between macroscopic quantum effects and the underlying vacuum structure.
It really makes you wonder, doesn't it, if we can now probe this subtle interplay between vacuum forces and superconductivity with this kind of innovative precision. What else might we find? Could there be unexpected connections to other deep questions? Maybe new angles in gravity, or ways to engineer or stabilize novel quantum materials. It just opens up the imagination about what exploring quantum phenomena on this scale with this new level of control might ultimately reveal.